having me here. I've really enjoyed the conference. The talk, I'm going to present a paper. This is joint work with Daniel Kim at Pennsylvania. And the paper has really two components. It has an econometrics component, which is about measurement error and about basically recovering bounds on coefficients when you think that the data is error-laden and when you don't have exclusion restrictions imposed. And then there's a second component to the paper, which is basically looking at the returns to college selectivity and characteristics. So let me just motivate things with the context of this empirical setting. So I was passing by the career placement office at UVA, and I came across this article from the Wall Street Journal. So obviously, the decisions of where and whether to pursue a college degree are quite important. And this Wall Street Journal article was recommending, offering advice, saying that a big name doesn't always matter much, to be mindful of debt, that you don't need to major in business, and so on and so forth. And with a quick search, you can see that there's a whole industry of sort of offering advice on this important topic. So a New York Times article suggests to favor schools with higher percentages of foreigners. Answers, does brand matter inconclusively? An NPR commentary says that college size matters, that a name brand won't guarantee you success. An Atlantic article talks about small schools with high concentrations of computer science and engineering students near large cities with thriving technologies, dominating the list of schools with highest earning graduates. And so what do we know about the empirical evidence on the financial returns to college selectivity and characteristics? So obviously there's many non-pecuniary returns of interest here, but we're going to focus on earnings as one outcome that students may consider. So there are a couple of challenges that the literature discusses. One of them is the limited availability of data in the US, particularly on individuals that matches their earnings with the characteristics of the education that they receive. So if you contrast, that with, for example, a recent study that uses Norwegian administrative data, in that context, they know every student's application record, where they went to, where they got rejected, what were their preferences and their order of applications. And that's not available in the US, so the studies typically rely on survey data that focus on a narrow subset of US colleges, or look at regressions continuity designs where they examine a particular college and whether you got into that college or not. Basically, they compare people around the cutoff. The second challenge, which has to do with endogeneity, so sorting based on unobserved scale and characteristics that the individuals may have. And so, if you consider the possibility that people with higher unobserved skill, so the term used in literature is ability. People with higher unobserved ability may earn more and may sort into colleges that are more selective or have particular characteristics. And that endogeneity is going to make it difficult to figure out the effect of selectivity from, sort of separating the association from the causation here. So what do people do? So they model college choice. That's one possibility. They match students based on observed characteristics. For example, in Dale and Kruger, what they do is they look at the application records that students have. Where did they apply? So they compare people who applied, who got into similar places but attended to different colleges. Or they, as I said earlier, compare individuals right around the admission cutoff. So the findings are mixed. Some papers find a strong evidence for a large effect of attending a more selective college, and others don't. So what are we going to do? Just an overview of the results. Recently, the Obama administration released the college scorecard data. So this is a quite sort of a rich, comprehensive data set on post-secondary institutions in the US. It's an aggregated data, so it's at the institution level, so we don't get to observe actual students, but we get the aggregates at the institution level. But it contains a lot of information on the institution, on the student body, the affordability of the college, the admission and academic attributes, and the earnings outcomes. So we're going to use this data set and try to see what we can learn from it. We're going to follow the literature in defining selectivity as the average SAT equivalent score of the enrolled cohort. So those are the students who got admitted and enrolled at a college, and we're looking at their average SAT score as a definition of selectivity here. While the data has several limitations that I'll mention, hopefully, if I have time, it is the first nationally comprehensive data on students' post-enrollment earnings at nearly all post-secondary institutions in the US. So what we're going to do is we're going to use a very simple model. We're basically going to write down a model of log of average earnings as of students, so 6 years after enrollment, as a function of the college's selectivity and a set of characteristics that has been considered in literature about the college and the cohort sort of characteristics. But we're also going to allow this equation to have an unobserved ability term that enters into that equation, and that's the story that I mentioned earlier about potential sorting. Now, we're not going to restrict how the college characteristics and the unobserved ability depend on each other, statistically speaking. And so we're not imposing some exogeneity type restriction here. But to get around the issue of the unobserved ability term, we're going to use the average SAT score as an error-laden proxy for the average unobserved ability. The caveat here is going to be that, remember, that's also the measure of selectivity. So we think that that also has a direct effect on the outcome. That's what's been considered in literature. And so we're using the average SAT score here in two ways. In one way, it potentially matters. If you went to a prestigious school, maybe you'll earn more just because you went to that school in terms of an impact of going there. But we're using that variable as well as a measure for the unobserved characteristics of the cohort. So, and what we're going to do is we're going to do a sensitivity analysis. We're going to basically restrict two dimensions, impose two restrictions on the data and sort of see how the results change as we vary these restrictions. So the first one is going to restrict the extent of the measurement error and how we think SAT proxies ability. We're going to change that restriction and see how the identification regions are going to change as a result of that. And the second thing is we're going to restrict the direction of the effects. So we're going to impose sign restrictions. So in particular, we may say we think both the unobserved ability and the college selectivity drive outcome in the same direction. So specifically, this is really the model that we're considering. It's very simple. We have y is the outcome equation. X are the covariates that we're going to consider about the college characteristics. U is the unobserved ability, and W is our proxy for the unobserved ability. So it's an error-laden proxy for U. And we have an unobserved term, which I'm going to call a disturbance, that's not causing any trouble. So the source of the difficulty here in this model is really the fact that U is unobserved. If you look at this model, you'll notice that in relation to the classical results about measurement error, the sort of the feature that should show up here is the fact that this phi coefficient is not 0. And so we're allowing the proxy to directly have an impact on the outcome. And that leads to differential measurement error in the sense that even if I told you the unobserved ability of the cohort, you're going to think that selectivity may have an impact on earnings beyond its proxying for the unobserved ability here. So we're going to allow for a setting that occurs when W is not merely a mismeasured version of U, but is a separate variable acting as a type of proxy for U, essentially. We're using this framework here in this context, but obviously it could be relevant in other contexts when a researcher suspects that the proxy itself may drive the outcome, like in a medical test when I learn the test result and I alter my behavior, a financial market valuation where I take the financial valuation in account when I'm making investment decisions, and so on and so forth. So going back to what we know when phi is equal to 0, we already know that substituting the proxy for the latent variable is not harmless. So if you regress y on x and w, you have attenuation bias on the coefficient on u. So what we want here is to recover beta, phi, and delta. And when you set phi is equal to 0, we already know that just running regressions isn't going to do it. A key paper here is Klepper and Lemur that drives sharp bounds on delta. And so we can actually, we don't point to identify delta, but we can get a range where we know delta lives. And so the question we're asking is, how do these bounds change when we allow the proxy to enter the equation directly? So what if phi is not 0? So the first, what we're going to do is we're going to characterize the joint region for phi, delta, and beta, and rho. Rho is going to be the signal to total variance ratio, not of the covariates. I'll show you more specifically in a second, but that's just the variance of u over the variance of w after conditioning on the x's. So when we project this joint identification region on the separate components, what we're going to first find is that nothing is identified here. And so if you project these on the real line, you get back the real line. So the exclusion restriction for setting fees equal to 0 is quite crucial. If you move away from that restriction, you really learn nothing in this world. So to move forward, we're going to do the sensitivity analysis and work with two types of restrictions. The first one is in the same spirit of the Klepper and Lemur restriction. So what we're going to do is we're going to weaken the assumption that says there is no measurement error. SAT is ability. And we're going to allow for some measurement error by imposing an upper bound on the variance of epsilon, the variance of the error term in this component here in this equation. So we're going to place a bound on the variance, on the ratio of the variances. So for example, putting a restriction that says this kappa term is equal to 1 is going to say that, given the characteristics, we're going to say that at most half of the variance in the SAT score is due to noise after conditioning on the covariance. And we're going to play around with changing kappa and seeing the impact on the estimates that results. And the second one is we're going to weaken the phi is equal to 0 restriction by saying we're going to think either phi and delta have the same sign, so or non-negative, the product is non-negative or non-positive. And so in our context, we are going to entertain the idea that we think maybe average ability and selectivity go in the same direction, impact earnings in the same direction. We don't really, in terms of the econometrics, we don't really need to choose a particular configuration of these restrictions, but what we want to do is to establish the mapping from the assumptions that you're using to the conclusions that you get, essentially, to the identification regions that you get. So graphically, this is how the graph looks. We're interested in the effect of x of u and of w on y. X and u are freely associated. W serves as a proxy for u, but w may have a direct effect on y. And we're going to try to basically figure out what the effects of u, of x, and of w are, or at least what we can learn about them in this framework. So here's a summary or a brief sort of an outline of the basic findings. Is we find that under, conditional on the college characteristics and the composition of majors at the colleges that we have, and under the assumptions that kappa is set to 1 and phi and delta are restricted to be non-negative, we have that 100-point SAT increase in the average SAT score, roughly the difference between Stanford and Boston College in our sample, leads at most, so it could be as small as 0, so it's an upper bound, 4.8% increase in the average earnings 6 years after enrollment. We're separating two components of X that have been discussed in the literature as particular sort of explanatory variables for why the selectivity matters. So instructional expenditures and completion rates. If you condition on these two variables, you can narrow the upper bound to 2.8%. We also get tight bounds on the return to college characteristics, which this is a sort of a rich set of the vector X, and I'll talk a little bit about that later. But a thing that emerges here is the importance of accounting for the composition of majors. And in particular, once you account for the majors, you can see that some of the apparent effects are now, the bounds are now changing. In particular, whether a university offers a graduate degree and the gender earnings gap in this case. So this is basically the overview of the paper. And the remaining time, I'll try to show you some of the details. I'll talk about the data generating assumptions, about identification. I'll probably show you the identification results in terms of a numerical example. So just show you some graphs that show you what's going on here, estimation and inference, and then the empirical example that looks at the returns to selectivity and characteristics. So as I said, it's a very simple setup here. The data we get to see is X, Y, and W. That's the data that we have. We're going to assume that this data is generated by a structural system, which are these two equations. It's a linear homogeneous coefficient type equation, so it's a simple model. The key issue here is that we only get to see Y, X, and W. We don't observe data on U, on the error, obviously, and the disturbance eta. So part of the assumption A1 is that it decomposes W into a signal, so the sort of the average ability component, and a noise, which is the epsilon component. We're going to maintain the classical error in variables assumptions. And so, again, sort of the textbook assumptions. These say that the source of the identification trouble is the fact that U is unobserved. And so eta itself is uncorrelated with X and U. The error is uncorrelated with X, U, and eta. So if you set phi is equal to 0, these are the classical error in variables assumptions. And in that setup, given that this is a parametric equation, if you use higher order moments, you could point identify these objects. But we're just working with uncorrelation assumptions here, so we're not going to use these. The other thing we're going to do is we're going to get rid of phi is equal to 0, and that's going to lead to the second difficulty, which is the fact that now the measurement error is differential as opposed to non-differential. So the traditional assumption has been that, or the sort of more commonly used assumption has been that once you know the average ability, the average SAT score shouldn't matter, and we're basically allowing for the average SAT score, the selectivity itself, to have a direct impact. It may be 0, but maybe it's not. So in that case, even if you assumed a bunch of other unobserved terms have mean 0, conditional, and other characteristics, you're always left with this epsilon phi term. And so unless if phi is equal to 0, there's that added difficulty here. So an important point here is the dimensionality. We're focusing on a scalar U and a scalar W. And even in the case when phi is equal to 0, as shown in the Klepper and Lemur paper and in Bollinger, if you move to the vector case, the extension is not trivial, and you need additional restrictions, additional sign restrictions to get non-trivial bounds. So we're going to stick to the scalar case in this context and leave these extensions to other work. So some notation, the sigmas are variances and covariances. The R terms are IV regression coefficients. So these are literally, whenever you see an R, I'm just referring to the IV coefficient on B when I run an IV regression of A on B using instrument C. These are the IV residuals. When C is equal to B, these are going to be just the OLS estimates in the population. And the script R is the R squared from regressing A on B. And so these refer to stochastic objects, so regression coefficients, regression residuals, and so on. Now, one useful thing here is we can project on X, and if you do that, and you use the star notation to refer to the net of X residuals here, then you can transform the model into these two equations right here with the starred variables. Our object of interest is going to be phi delta and phi plus delta, and there's a mapping that brings you from phi plus delta to beta. So if you know phi delta and phi plus delta, you can recover phi delta and beta. So we're now going to work with the projected system right here and ask how can we recover, what can we learn about phi and delta and phi plus delta. So here are the two restrictions that we're using. The first one is this R1 restriction. These are our auxiliary restrictions. Is a bounded net of X noise to signal ratio. This is an assumption that says rather than assuming that there's no measurement error, we're going to assume that the extent of the measurement error is bounded above by a constant kappa, particularly the ratio of sigma epsilon to sigma u star, where u star is the u term net of X, is bounded by a kappa. This is going to give you an upper bound on the share of the variance that's due to the measurement error. So an upper bound on how much the SAT scores could be error-laden. We're going to impose R1 throughout and let kappa go to infinity to see what happens when we get rid of that restriction. In that case, R1 is not binding and you're not imposing it. And the second restriction that I mentioned earlier is the sign restriction. We're going to call these R2 plus and R2 minus depending on which direction they go. So this is weakening the phi is equal to 0 exclusion restriction. So a few comments about R1. You could link R1 to the unconditional ratio, the reliability ratio of the data. So what rho is doing is it's placing a lower bound on this ratio of variances right here. Using this formula, you could see that if you were to just look at the R squared from regressing SAT on ability, it's going to be a weighted average of the R squared from regressing W on X and 1. And rho is going to be the ratio that we're imposing a lower bound on. So in other words, R1 is equivalent to imposing a lower bound on the reliability ratio. You can work with either of these two restrictions, either with imposing a kappa or a tau, and there's a one-to-one correspondence here. The researcher can choose either. Basically, if you look at this equation here, what we're doing is we're saying, if we think the covariates predict SAT by, this is the R squared that we could estimate, how much better do we want to allow ability to predict the average SAT score? And we're going to let you place a lower bound on that. You can do it either unconditionally or conditionally on the x's. So for instance, setting kappa is equal to 1 says that the R squared from SAT on ability needs to be at least half as close to 1 than the R squared that you would get by regressing SAT on the characteristics, the x's that we have. The closer you let the R squared from W on U to be to the R squared from W on X, the more error you allow, but also the better you allow X to predict ability. So the more ability and the characteristics become collinear, essentially. Brief digression, if you impose some zero exclusion restrictions on the x's, you could use an IV to point identify phi plus delta and beta 2, but not phi alone or delta alone. We're not going to work with these restrictions. So without any exclusion restrictions, what do we know? So if you regress y on W and x, you get a weighted average of phi and phi plus delta, and the weights are going to be rho, this ratio that we are going to place a restriction on. So if there's no measurement error, rho is equal to 1, and now a regression recovers phi plus delta and beta. If you think U and X are perfectly collinear, so you think you're able to predict ability perfectly, then you can recover phi by noticing that rho is equal to 0. But we also know something else. We know that there needs to be some, a non-negative restriction on a variance term. So that gives us this lower equation, this lower inequality here. So we're going to work with these systems, with these inequalities and equalities, and try to see what we can learn about phi, delta, and beta. So this theorem basically points out that you could write all of the other unknowns in the system, delta, beta, and this psi squared. That's just the variance of eta, the unobserved, the disturbance scaled by the variance of W given the x's. You could write everything as a function of phi and rho. So you could now reduce the problem into a problem about what can I learn about phi and rho. If phi is 0, you have the exclusion restriction. If rho is 1, you have the no measurement error. And now we're going to work with, so we're going to derive the identification sets. I'm going to show you a little bit the math of the structure here, but I think it's easier to show you an example. But just to give you a sense, we're going to work first with the case when phi is equal to 0. That's going back to Gini, Frisch, Klapper, and Lemur, and Bollinger, to cite a few papers here. And we know we get attenuation bias. We know we get these bounds. And so the structure of the results are going to be, first we're going to look at rho, phi, delta, and beta. And we're going to say that these coefficients, this vector, needs to satisfy this system of inequalities here. In this case, phi is equal to 0 because we're imposing that exclusion restriction. Then we're going to take this higher dimensional set and project it on each of its components. And so we're going to get the sharp projections on the rho, delta, and beta spaces. So these sets are sharp. So the joint set is sharp in the sense that for any element of the set, I can construct unobserved variables that could have generated the observed data. And the projections are sharp in the sense that any element in the projected sets, you have a corresponding element in the joint set that could have generated it. And then using these sets, you could say, well, when do I get point identification? You could sort of examine the conditions. What if I get rid of R1? So I let kappa go to infinity, and you can sort of go back to the standard bounds in this case, and so on and so forth. We're going to do the same when we have differential measurement error. So now phi is allowed to be non-zero. And in this case, all we're doing is we're imposing R1. Again, same structure. You get the joint set, and you get the projection. In this case, you learn nothing about phi and delta, but you can learn something about rho and beta under R1. You could ask what happens when I get point identification, what happens when I let R1 go to kappa go to infinity. You could add R2 plus. Now you're adding another condition here that says phi and delta need to be positive. This is what this inequality is conveying. Same structure, so you get the joint set, the sharp set here, and then the projections, the sharp projections that tell you what the parameters will be. Again, you could do the point identification and letting R1 not bind. And last, you can do the same thing for R2 negative. And so we're going through all of the configuration of the assumptions that we can essentially establish. So let me show you an example to just show you what these sets are doing. So take these equations that we have, and we picked some parameterization here. So we picked values for phi, delta, beta, and so on. This is a numerical example that satisfies all of our assumptions. The ratio here of the variance of epsilon to the variance of u star is 0.461. So any kappa above that would be a valid restriction. So what we're going to get, a set for, in this case, a 5 by 1 vector. We're going to get a joint set for all of these coefficients. And so what I'm going to show you are slices of that set in 2 dimensions. So this would be the rho phi dimension. Phi is the coefficient on W, and rho is the conditional sort of reliability ratio, if you like. The truth is the yellow dot, the yellow cross. This would be the classical bounds that set phi is equal to 0. Obviously, they don't contain the truth because they're not imposing the right assumptions. This would be the bounds that impose only R1, so no sign restriction in that case. The shading in these pictures denote the strength of kappa. So as you let the kappa go to infinity term, you get these lighter shades. And as you get tighter and tighter kappa, you get the denser, darker shades, which are nested within the lighter shades, essentially. This, in this case, obviously the truth is contained in this sharp region. This is what happens when you add this positive restriction, which is correct in this case. This is what happens when you add the negative restriction. Now you get this disconnected set, and the truth is not contained in here. So this is in the phi delta space. You could show the, this is in the phi rho space. You could show the phi delta space, and same story goes essentially. And you can show the beta 1, beta 2 space, and again, the same idea goes, right? So this would be collecting all of these together. This is the classical phi is equal to 0 bounds. This is the negative sign, so both of these are incorrect, and in this parameterization, they happen not to contain the truth. Both of these restrictions are correct, and they do contain the truth as the theory shows. So what we're doing is we're basically deriving analytically, we're projecting these sets onto each of the components here to get the sharp sets. So we're giving you the analytical expressions that allow you to recover the bounds that you would get if you were to project these sets. And so how do I do estimation? So every element of the sets here, every set is a collection of elements, and each element is a function of some moments, regression coefficients, and so on and so forth, and a nuisance parameter that lives in a set that I know, like 0, 1, or -1, 1. And so to get a consistent estimate for the set, we can estimate R consistently and use a plug-in estimator to get a consistent estimator for the set itself. So under standard conditions, if you have a law of large numbers and a central limit theorem, you can get a square root and consistent estimator here, an asymptotically normal estimator R hat. We're going to use that and plug it into the expression here. Now, to construct confidence regions, what we're going to do is we're going to basically take every element in the set, construct a 95% confidence region for that element, and then take the union of all of the confidence regions over all of the elements in the set. That's going to be a confidence region for a partially identified parameter in the region that we have. There's one caveat here is that some of the functions theta depend on a sign that needs to be estimated, and so you may want to adjust for that pre-estimation. So what we do is we point out that the sign is equivalent to learning about a partial correlation coefficient. So we add that into the nuisance parameter set, and we estimate the confidence region for it, and now we take the union over the confidence region that we have crossed with the known set. And so we adjust that. In our case, this alpha 2 term that we take to construct the confidence region, you can estimate this sign very precisely, and so you can make that very, very small, and the adjustment can be negligible in this case. So in the remaining 10 minutes or so that I have, I'll try to give you an overview of the results. So in the literature of the empirical results, so in the literature, so I said there's mixed evidence. So some studies report an evidence for a positive return to college quality. The first paper, the Brewer et al. Paper, talks about a significant wage premium for attending an elite private college 6 years after graduation, after enrollment. Some propensity score matching work finds a similar thing. So this is the Black and Smith paper, but there's high standard errors in there. The regression discontinuity design is looking just at a flagship university, I think in Florida, and comparing it to the remaining or to the other universities, and finds that 10 to 15 years after graduation, white men earn 20% higher if they attended the flagship university than if they didn't. Of course, we don't know where they went if they didn't attend this university, but on the other side, Dale and Kruger basically look at individuals who were admitted to equally selective colleges but attended different colleges and find that they earn comparably. And so in that case, we don't find a very strong evidence for a large return to college selectivity. And the other paper, which is not on US data, points out that the return to selectivity seems to be small relative to the return to the field of study. And so it seems they find that the field of study has a larger impact on earnings. So what we're going to do is we're going to use this college scorecard data to try to apply our framework, and see what we can learn from it. This is, as I mentioned, an aggregated data set. It's aggregated at the level of the institutions. It's drawn data from the Integrated Post-Secondary Education Data System, the National Student Loan Data System, and Department of Treasury tax records. And it has, characteristics of the institution, the student demographics, admission, academic attributes, affordability, and earnings outcome, among other things. So I should point out that there are limitations to this data, one of them is that this data is looking at Title IV students. These are students who receive federal loans or federal aid, and so the authors or the work that went behind this data, the CEA, the Council of Economic Advisors, they say about 70% of the graduating post-secondary students are Title IV students, and they argue that they seem reasonably similar to the overall population. There are issues with the definition of the institution. Some institutions that are very large aggregate differently across different campuses. There's also issues with the definition of a cohort. Sometimes cohorts differ in how they're defined. The extent to which all of these issues are going to matter to us depend on how these aggregate features change in the short run. At any rate, we're not going to tackle these imperfections directly here. We're basically going to focus on how average SAT could be a proxy for ability in this case. Our sample is going to be the most recent cohort. So these are the students who enrolled in 2007, graduated in 2011, and were non-enrolled and working in 2013. So we're looking at a short-run type return. We have 1,165 institutions. These are the institutions that are bachelor's degree. They're either public or private nonprofits, so we're removing the for-profits. We're looking at the main campus of an institution, institutions that remained in all years from which we draw data in our sample, which is most of them, I think, and then we're dropping observations that are missing, including some places that didn't report the SAT results. To get a sense of whether things match your priors, the 5 most selective institutions in our sample are Harvard, Princeton, Yale, MIT, and Dartmouth. If you look at the public institutions, the 5 most selective are William & Mary, Georgia Tech, SUNY Geneseo, UVA, and University of Michigan. The standard deviation of the SAT score is about 120, roughly the difference between Stanford and UVA. So I won't show you detailed tables. So we worked with a baseline specification, and we considered 2 other specifications that extend that, so they're nested. Y is the log of mean of earning, W is the average SAT equivalent score of the cohort. X always contains, in the baseline specification, X contains the institution characteristics. So this is the region, locality, whether it's minority serving, a women-only college. We don't have men-only colleges in our sample, whether it has a religious affiliation, whether it awards a graduate degree, and whether it's public or private, so what's its control. For the student body characteristics, we look at the size, the composition of racial and gender composition, family background variables such as the percent of post-secondary educated parents and the log of average family income. And the third feature is the affordability, so the average cost, the net price, and the percentage of students who have loans or Pell Grants, as well as the median debt for the students. So we then considered 2 other specifications. The second one is basically adding the composition of major, which we think plays an important role in making this comparison here. So the first one is not taking into account that different schools may focus on different disciplines. And the last specification is looking at these two variables that people think may channel what selectivity means here. And one is the instructional expenditure, so how much does the school spend on students? And the second one is the completion rate, how much does the school retain students? Our baseline specification for kappa is that it's equal to 1. That's saying that at least or at most half of the variance in the SAT score given the covariates is due to the measurement error. If you regress the SAT score on Rx, you get a reasonably high R squared, so 81, 86, and 88%. And kappa equal to 1 assumes that ability is going to predict SAT half as close to 1 as the covariates would. But of course, we're going to vary kappa, so we consider setting a lower bound on the reliability ratio directly, which is 90%. And we also let kappa range from 0 to 30, so 0 being that there's no measurement error, 30 being that essentially the SAT score given the covariates is just measurement error. Yeah, is actually perfectly explained. Yeah.
I was wondering whether you can gain anything from adding higher order polynômiograms in W? Something to kind of,
So I think that goes to the footnote about moving away from the scalar case that I mentioned earlier, and I don't think it's going to be as straightforward. I mean, the moment you move away to the vector case, I think a lot of things could happen. The vector latent variable, essentially. So let me give you a summary with the next 5 minutes of what we find. So as I mentioned earlier, under our assumptions, a 100-point increase in the average SAT score leads to a bound of 0 up to 5%, with a fairly, a confidence region of 0 up to 6.1%. If you account for these instructional expenditures and completion rate, you can narrow that to about 2.8% with a confidence region with an upper bound of 4.2%. So a big sort of a general summary here on the X characteristics. So for the institution, we can't rule out that public versus private or institutions that offer a graduate degree versus those that don't, we can't rule out that they have similar mean earnings. So the bounds contain 0 in this case. For the student body characteristics, we find that increasing the diversity, so share of minority and an average family income has a positive effect on the average earnings. We do pick up the gender wage earnings gap, so the increase in the share of female or dependent students has a negative effect on the average earnings. For enrollment size, share of non-resident aliens, and family background variables, the bounds are inconclusive. For the affordability characteristics, Pell Grants and median debt, we have negative bounds that suggest a negative effect on these, but we can't rule out that the average cost, the net price, and the percent of students with loans, that the bounds contain 0. So to give you an example, so, also for the composition of major, if you shift the distribution of majors with 1 percentage point away from the social sciences and toward engineering, the bounds are about a 0.25% increase in average earnings. A shift toward education gives about a minus 0.25%, although the confidence regions are a bit larger here. If you compare the coefficient on the female variable with or without conditioning on the major composition, you'll notice that it changes from about minus 1 percentage point increase in the percentage of females leads to a minus 4% drop in the earnings. If you account on the major composition, you almost half that to 0.2%, but obviously the gap is still there, but you explain a part of it essentially. Here's the sensitivity analysis. As I said, we vary kappa from 0 to 30, and we get fairly tight results around the regression estimate. So, so for example, these are confidence regions and bounds as I let kappa go from 0 to 30. This is the female coefficient, and so you can see that it takes a lot to get that bound to vary. In particular, if you want it to include 0, you have to push kappa up to 9, 29, or 15, and the other specifications. This suggests maybe that measurement error is not that, maybe the measurement error in how SAT proxies ability is modest, or maybe ability has a small effect on mean earnings. At any rate, to sort of, discuss the results, obviously we can inherit some of the limitations of the CS data. So the CS data has some limitations which may be affecting our results. We are assuming quite a bit here. So we have a linear specification, we have homogeneity in the coefficients, we have endogeneity due to one U, and so one has to take that into account when interpreting the results. I think relative to the literature, two favorable things in here are, one is we're analyzing this new CS data, which is pretty comprehensive data, and two, we're weakening some of the assumptions. So we're allowing for measurement error, we're removing the exclusion restriction, and we're able to learn something without assuming the exogeneity of instruments or of having conditioned on covariates that ensure exogeneity essentially in here. So I'll stop here, given my time constraints. The restriction. Yeah, so, is this about the Title IV, right? Is that, yeah. It's possible. I mean, it's possible that this subpopulation differs from very affluent, students. And unfortunately, we can't do much about that. So, I mean, if we believe what's in the CEA report, their claim is that this seems to be comparable in terms of academic achievement and whatnot. But we don't have the data they're comparing things to, and so we don't, we can't, learn from that. I think part of the reason the Title IV students are here is because these are the people who we have tax records on, and so, but I mean, it's possible that this group may differ. No.
The only thing I would think to link to the previous talks that sort of Ed and Angus wanted to be more, have more humility in presenting things. I think this kind of trend towards more partial identification and sensitivity analysis is kind of building that sort of sense of humility, not all the way, but at least part of the way, making us self-conscious about sort of what we can and can't identify. So I think, so in that sense, that's like you're talking is a really complicated way of saying that.
Thanks.
Okay. Rodrigo Pinto is our last speaker. By the way, Elias has been doing a great job all day